All right, welcome everybody. This is going to be Demystifying Ethereum Assembly, a practical 0 to 1 guide. So my name is Joshua, or JT Riley. I'm an EVM smart contract engineer. And so a little bit about why I'm here giving this presentation. There's a really big gap between the intermediate Solidity developer and the wizards that can do the assembly black magic, right, that we see in some popular GitHub repos. So I kind of went through this the hard way, reading through as much documentation and as many papers as I could, and hopefully I've condensed this down enough that everybody here can kind of pick this up a little bit faster. Or maybe if you already know this, maybe this will kind of reinforce, or you can learn new things. So this workshop is going to be pretty interactive. So if anybody has questions, if I go over something and maybe it's not clear, feel free to stop me, raise your hand, ask questions. We're going to get to the bottom of pretty much anything you guys have questions on today. So as we get started, section 1, obviously, understanding the Ethereum virtual machine. Here is a link tree. It's going to be the link tree / EVM assembly. And so this is going to have some useful links throughout this presentation. The most important one, for you to be able to follow along and kind of play with these things is called evm.codes. So I'm going to be using that as well periodically throughout. Basically what this is a fantastic resource. It's got everything you need to know about instructions, and then it also has a playground, and that's where we're going to be demoing some of these things so we can really visualize and internalize what's going on. So first up, we're going to talk about the instruction set. So the EVM is a stack-based virtual machine with a relatively small instruction set. And these instructions can be categorized by one of the following, roughly. First is stack instructions. So these are things that have to do with the stack, the values that are on the stack, and swapping, duplicating, things like this. Arithmetic instructions are addition, subtraction, pretty basic stuff. Comparison instructions tend to compare two values and then push 0 if it's false or 1 if it's true. Bitwise instructions has to do with like bit shifting and other really cool stuff. Memory instructions are going to be interacting with the memory in the EVM, which we'll get into a little bit more on that page, and then contextual instructions. So these are like reading and writing to the environment, to storage, and other things like that. So first we have stack instructions. So stack instructions involve manipulating the position of a value on the stack, or values on the stack. So push in value basically pushes a value to the top of the stack where n is the byte size of that value. Pop will pop a value off the top of the stack. Swap in will swap a value on the stack with another. And then dupe in will actually duplicate a value based on the index. So as an example here, this is mnemonic bytecode. Basically, it's just a human-readable format of what the actual EVM bytecode is. So this is at the lowest level. So first we have push 1, right? So we're pushing a value of size 1 byte. The value is going to be 1. And over here, these orange bits here, this is actually just comments to kind of represent exactly what the stack should look like after any given instruction. This next one, it's going to push 1, and that value of 1 byte is going to be 2. So now we have 2 and 1 on the stack. We can do swap 1, which will swap. We have dupe 1, which can duplicate the first value on the stack. And then from there, we just do pop until we run out of values on the stack. So if you guys want to open up the evm.codes website, this is evm.codes/playground. You can also find it in the link tree. So first we're going to do basically pushing the number 1 to the stack, right? So we push of size 1, the value is going to be 1. We'll do the same thing with the number 2. We can do it with 3. And then we can start playing with this, right? So let's say we want to swap the top instruction, or sorry, the top stack item with one that's 2 items down from that. So we can do swap 2. And whenever we run this, we can basically step through every instruction here. So the first one pushes the 1 to the stack. The second pushes the 2 to the stack. You can see the stack represented down here in the bottom right. We'll do the same for 3. And then swap 2 should swap the number 3 with the item 2 items down from it. And there we go, and it swaps. So from stack instructions, we're going to go to arithmetic instructions. So of course, add, we'll add two values. Sub, we'll subtract two values. Mul, will multiply two values. Smul does the same thing, but it treats the number as a signed integer. And so what this means is that the number can be represented as positive or negative. Same thing with div. Div is divide, and then sdiv treats them as signed integers. Mod will actually do the modulus, so the remainder after division. exp does exponentiation. And then we actually have some instructions, add mod and mul mod, that will consume 3 items and basically do addition, then modulo, and then multiplication, then modulo. And so here's our arithmetic example. We push a 1 to the stack, we push a 2 to the stack, and then we call the add instruction. It consumes the 2 and the 1, adds them together, and pushes a 3 to the stack. Next, we'll push the number 2 to the stack. We'll duplicate it. We'll duplicate the second item on the stack, right? So now we have 3, 2, 3. And then we'll multiply, which will give us 3. We'll multiply, it'll give us 6. And so now the stack is 6 and then 3. And then we'll divide those, which will give us 2. So hopping over to the playground again. So we'll push 2, push 3, multiply, and let's push, let's say 5, and then add. So as we step through this, we'll see the 2 is pushed to the stack, then the 3. Those are multiplied, so the 2 and 3 are consumed. There's the 6. We push the 5, we add it together, and that'll give us 11. Now this looks like B because this is actually an hexadecimal representation. So instead of going 1 to 9 then rolling over, it actually goes 1 to 9, then A to F, and then it rolls over to the next. So next up, we have comparison instructions. So what this will do is pop 1 or 2 values from the stack, perform a comparison, and then based on the result, it'll either return true or false. Those are actually reversed. If it pushes true, it's going to be 1. If it pushes false, it's going to be 0. So LT will push if the top value is less than the second value. SLT, of course, is with signed integers. Greater than, or GT does greater than. So if the top value is greater than the second value, then we push 1. EQ will compare and see if the top 2 items on the stack are equal. And then is 0 will push a true to the top. It'll push true if the top value is 0. Now, something to note about is 0, you're going to see this a lot in Yule files and other low-level assembly stuff. Is 0 is commonly used as a sort of inverse operator, right? So it's same as the exclamation point in front of a Boolean. So as a comparison example, we push 1, and then we push 2. We'll check equal. Of course, this is going to push false. That's going to be 0. And then we can use is 0 to invert that if we need to for whatever reason. So it'll invert it to true. And then at the end, we pop there. Next up, we have bitwise instructions. So bitwise instructions pop 1 or more values from the stack and perform some bitwise operation on them. Now, AND performs a bitwise AND on the top 2 stack values. So what this means is that every bit, or every 1 or 0 within this number, if you compare 2 values, the result is only 1 if both bits are 1, right? So if, actually, I think we'll have a bitwise example in a second, but basically, it's only a 1 if the 2 bits are 1. An OR operation will be 1 if either of the 2 values are 1. XOR is exclusive OR, so basically it will only push a 1 if one of the 2 values is 1, but not both. NOT will invert it, so whatever the value is, it'll invert that if it's 0, 1, if it's 1, 0. And then SHR and SHL will perform bit shift operations where we can shift the bits left and right. So as an example, over here on the left, there's a little bit of encoding here just showing you, basically what these numbers look like in binary format. And then on the right, we have push 1, push 2, familiar with this. But the SHL operation is going to shift the number 1 by 2 bits, right? So it's going to move it over 2, so we can see here it starts at 0001, but after it moves over 2, it's going to be 0100. And then we can do the same thing to shift it right. So we push another 2 to the stack. SHR is going to shift it back to where it was. And then the not instruction, as you can see, it's going to flip every bit. So 0001 becomes 1110. So memory instructions can read and write to a chunk of memory. Now, memory is this linear data that can be read and written to during the execution of a program. So it's a different place in the stack. It's good for storing things like arbitrarily sized values and things like that. So mstore will store a 32-byte or 256-bit word to memory. Everything in the EVM operates on these 32-byte words. So we can store a full 32-byte word. We can actually also store a single byte or 8-bit word to memory. And we can also mload. So what this does is loads a 32-byte word from memory given some index in that memory. So here we're going to push the number 1, then the number 0 to the stack. And what mstore is going to do is consume these 2, and it's going to say at position 0, we're going to store the number 1, and it's going to be padded out to the full 32 bytes. And so if we basically, after we've written to memory, if we push a 0 to the stack, or if we push any index in memory to the stack, we can call mload. It's going to consume that index and then return to us the value there. So in this case, pushing 0, and mload is actually going to pull out this 1. We'll go ahead and do an example for this one. Zoom in. Is that better? Cool. So we'll push the number 1 to the stack. Wait. Right. We'll push 1 to the stack, then we'll push 0 to the stack, and mstore is going to treat the 0 as the index and the 1 as the value. And when we want to retrieve this later, we can push 1. Oh, sorry, push 0, and then mload. And so if we step through this, we'll see the stack has a 1, then a 0. mstore is going to put in memory that first word is a 1. And whenever we want to load from this, we start at index 0, mload, and it's going to push that value back onto the stack. Now getting into context instructions, specifically the ones that read from the local context. And this is not a comprehensive list, there are actually quite a few, but some of the important ones, caller pushes the address that called the current context. So if you're familiar with Solidity, this is the same thing as message.sender. We have timestamp, which pushes the current block's timestamp. Again, same thing as block.timestamp. Then we have other things like static call, which can make a read-only call to another contract. So if there's a function that sits on another contract, we can call that through static call, and as long as it doesn't write to persistent storage or doesn't update the state of the EVM, then we can read from that. Call data load can load a chunk of call data into the current context. And so what the call data is basically the data that is sent to your contract to tell you a little bit about what function to execute, what arguments it has, and things similar to this. So call data load can actually pull some of that data for you. sload can read a piece of data from persistent storage on the current contract. So contracts can only read their own storage, but basically we can read any slot using sload. So as a quick context example, we can use the caller instruction, and it'll push that message sender to the stack. We can, for example, let's say we want to see if the caller is an owner of a contract, right? And let's say the owner is stored at slot 0 in storage. What we can do then is we can use push 0 and then sload, and that's going to load from the first slot whatever data is there. In this case, it's our owner, and then we can compare them by using equal. Right, so this is like the simplest representation of how to check if a contract is owned by somebody. Next, we have the context instructions that can write. And again, non-comprehensive, lots of stuff going on here, but some of the really important ones. Store can store data to persistent storage. Log n can append data to the current transaction's logs, where n is the number of special indexed values in the log, right? So if you've written Solidity, you see the events, you see sometimes that keyword indexed. All of these are actual indexed topics within this event. Now, something to note here is in Solidity, you can only have 3 indexed arguments in an event, but you can actually have up to log 4. And the reason for this is the very first topic in any log is actually the signature of an event, right? So it's basically just a SHA-3 hash of this event's signature, which we'll get into a little bit more in a moment, and then the rest are the index topics that you specify. Next is going to be call. So it makes a call to an external contract or to external code, but this actually can update the global state, right? So there's no restrictions on solely reading or anything like that. And then finally, we have create and create to. And so what these can do is actually deploy code to a new address, creating a new contract. So it's just a quick example of what you can write. For example, maybe we want to store the last timestamp that some specific thing happened, right? So we can use timestamp to push the block's timestamp to the stack. We can push a 0 and then store, and what that's going to do is store that timestamp at slot 0. So as a quick review, again, the EVM has a fairly simple instruction set. Most of what we've gone through, this is the bulk of what's actually going on under the hood. Of course, this section didn't cover every instruction, but it serves as a foundational understanding for Yule in the following sections. And so to the left, there's a simple contract that will store the caller's address and persistent storage, and then return true to indicate success, right? So stepping through this, we have the caller. We're pushing slot 0. We're calling store, so that's going to store the caller address and storage. Next, we want to store true or 1 in memory, and we can store that in the very first slot. So we'll push 1, which is true. We'll push 0, which is a slot in memory. We'll call mstore, which puts that in the memory. And then to return, we actually have to give it 2 arguments. 1 is the offset in memory, where we want to return data from, and then the second is the word size, or the memory size that we want to return. In this case, it's actually just going to be a single 32-byte word. So we'll push OX20, push 0, and then return. So any questions so far on the instruction set?
Can you give an overview of what the EPO cipher for your code? Like, I think on the right, what do they show?
Right here?
Yeah, like, I don't know if
yeah, so these are the representation of the instructions here. So here, we have like push 1, mstore, etc. Whenever we run this, we can actually step through. We can step through the instructions, and this is just a representation here. So we can. Right. So memory is here. Anything that's written to memory goes into here. Anything on the stack is going to be here, and then persistent storage, if any, is going to be down there, and then return value, if any. The stack can be 1,024 items. Now you'll notice in Solidity, you'll get the stack too deep error. And actually the reason for this is you can only swap and duplicate items 16 deep, right? So there's like a limit to how many local variables you can have, because Solidity actually stores these variables on the stack. So once it gets beyond that, Solidity doesn't have like an easy way to access that without losing information. So that's why you see that a lot. But yeah, it actually can technically go like way, way, way deeper.
The memory is frame dependent, right?
You know what, we'll just go ahead and I'll just go ahead and answer some of these quick questions right now while they're getting it set back up. So you mentioned like return data, right? Yeah. Okay, so there are actually special instructions to handle return data. You have return data size and return data copy. And so what you can do is whenever you actually make a call, you're not actually getting all that stuff back. Solidity kind of does a little bit of magic for you there. But basically what you can do is use the return data size instruction. It's going to give you the size of whatever was returned, and then you can use that to copy into memory.
There's like a special place of memory for return data that you can access in your frame. It's like this buffer in between the frames.
Yeah, so it's not stored in memory per se. Like it's only stored in memory whenever you explicitly do it. But yeah. of log 0. Oh, I guess we have the spec now. Yeah, actually, I don't want to get too far ahead of myself because we are going to do some more logging stuff, but I will go ahead and let you know. So basically, every log instruction, it takes up to the number of topics which are on the stack, and then it actually also takes a memory pointer and size. So even if we don't log any topics per se, we can actually just log like a big chunk of memory, and so that's one way that we can push data to that as an anonymous event. It should be within the event logs. I'm not exactly sure how the client libraries decode anonymous events. Obviously, it's a little unusual to see those nowadays, but yeah, we can, if we have time at the end, we can actually probably just break open a remix, see how it works. Are we good?
You mentioned there were two opcodes for the previous platform. What
Yes, so Create 2, one, it's, I believe, a bit more gas efficient, and there's actually a way to deterministically deploy to specific addresses from on-chain using Create 2. So it's just kind of choosing the utility of exactly which one you want to do. I hope this wasn't being live streamed. Are we good? Okay, cool. Sorry, I didn't want to go too far and then we have to go back. Great. So the hardest part is over. That was all the really in-depth stuff that will kind of give you this foundational knowledge for how to write Yule. Yule, thankfully, has a much higher level syntax. So what Yule is it's a low-level language that can be written in inline Solidity, or as a standalone language. You can write Yule files by themselves, but you can also use it as a compilation target. So it also acts as an intermediate language that you can compile other high-level languages to. Built into the language are most EVM instructions. These are callable as functions. There's basic control flow support and functions, well, user-defined functions. Now you'll notice whenever we start looking at Yule code that the stack is largely abstracted away, with the exception of a built-in pop function. So if there's some value that maybe you don't need that's returned from a function, you can just pop that immediately. So here we have the syntax overview. Now note that the keywords object and code are actually only used in standalone Yule files, so chances are you're not going to be touching this if you're just writing inline assembly. One other thing to note here before we start stepping through, Yule does have the if statement, but it does not have the else statement. So to handle multiple cases, we can actually just use a switch. And then the for loop functions very similar to what you see in other high-level languages. Obviously, the syntax is a little bit more funky, but it still does the same thing. So stepping through, starting at the top, we have the assignment syntax. So notice we have a colon and equal sign. So anything on the right side is assigned to the left side variable. If the variable is being newly declared, if we're not reassigning, then we need to use the keyword let. For the function syntax, we have the keyword function, the name of your function, any arguments, and then return variables from that. And so inside this function, you can see the letter C is already declared as a variable implicitly by saying this is a return value. And then colon equals will assign the sum of A and B. Right? So you can see this is a lot simpler to read than just pushing things and adding and things like this. Another thing to note about these internal functions is that the return is implicit, because return itself is actually an instruction that returns to the caller itself. That's not what this is doing. This is actually just manipulating some items, leaving an item on the stack, and then jumping back from wherever this function was called. So here we have the if statement. In this case, we're checking if A is equal to 0. And if this is true, then we can execute some code inside of that. In this case, we're just doing a revert. Below this, we have the switch. So the switch, we have a value that we want to compare against, and then each case is going to have the value that this variable could be, right? So case 1 means if A is equal to 1, then we'll handle that. Yeah, comments are wrong here. Case 2 is if a is equal to 2, and then default is our fallback, right? So if nothing else matches, if we need to just do some logic to handle the rest, we use default. And then finally, we have the for loop, right? So first we have let I, we're assigning it 0. So this is your I equals 0 part. In the middle, we have that comparison. So it's less than I and A. So as long as I is less than A, we're going to continue iterating. And then next we have I being assigned basically the sum of itself and 1, right? So we're basically incrementing it. And then inside of there, we can iterate and do our looping logic. So as a quick comparison to mnemonic bytecode, over here on the left, that was the code that we wrote a moment ago to store the caller in storage, store true in memory, and then return that from memory. And then over on the right side is how we do it in Yule. So a lot less verbose. And so now we're going to jump into Yule in Solidity. And this is really important because not very many people write standalone assembly files these days. Most of the time, you're going to be operating within the bounds of a Solidity file. So you need to understand what standards and abstractions Solidity has created. So some of these include the call data layout, which is a layout of that data that gets sent to your contract, the memory layout, the storage layout, event logging, and errors. So call data layout, per the Application Binary Interface, or ABI standard, the call data layout is as follows. So first, the first 4 bytes are the selector of a function. And basically, this is the SHA-3 hash of a function signature. And that includes the name and then any argument types within that. Next, after the first 4 bytes, each argument is padded to 32 bytes no matter what. Even if it's a UN8, it's always out to 32 bytes. If an argument is of dynamic size, then the slot where it should be is actually going to hold a pointer to a place in call data where the rest of the data is. So if we have, let's say, a string that's over 32 characters, it's not going to fit in a single slot. What we have is a pointer that says, okay, after everything else, here's where the string starts, and it's just going to go, and there are other ways to determine how long the string is. So as a quick visual representation, here we have the transfer function, which this comes from the ERC20 standard. So first up, we have the signature. So that's transfer. It has address, uint256. Now all we're actually hashing here is transfer, parentheses, address, uint256. That's the only part that we're hashing here. So we can see the hash, full hash digest here. We're actually going to clip that to the leftmost 4 bytes. And then the actual call data layout of one of these is going to be those 4 bytes followed by an address. In this case, it's going to be the target to whom we're sending the ERC20. And then the next is going to be the value, right? So even though these, like an address is not a full 32 bytes, we're still padding it all the way. Next is going to be the memory layout. Now this one is really, really important because per the Solidity documentation, the first 4 slots of memory are reserved. Now slot 0 and slot OX20 or slot 32, these are actually scratch space. So you can use these, whenever you're doing things in inline assembly. The OX40, though, is the free memory pointer. So basically what this does is as memory is expanding, Solidity will actually track how big memory is and when you can start adding new things to memory. And so what we'll actually do in some of this Yule code is we'll actually load from that to figure out where we can start storing things in memory. So it's really important, if this does get overwritten, you have to make sure that you have that variable on hand, right? So you can increment it if you store more things in memory, et cetera, et cetera. And then OX60 is the 0 slot. So the 0 slot is reserved specifically for whenever you're allocating new arrays, I believe. This is like basically a big no-no zone anytime people start overriding this. It's not a very good security practice. You have to be very, very careful about it. So I'm not going to recommend it, but we have seen it before. We'll probably take a look at somebody who does that a little bit later. Now, dynamically sized arrays will occupy 1 slot, which holds that pointer to where the actual value is in memory. There's another slot that indicates the length, and then every slot after that is reserved for a single element. So if you have 5 elements, even if they're small values, they're going to occupy 5 full slots. Now, byte arrays and strings are similar, with the exception that their elements are tightly packed and aligned to the left. So for strings, you're basically using a single byte value to represent a character. So in this case, on the byte level, it is equivalent to byte arrays. We're going to pack those as tightly as possible. So as a quick memory example, we're going to step through this. Now it's a function. It's pure. It's going to return some bytes, right? And so what we're going to do in here is first load the free memory pointer. So again, we're going to load from OX40. We're going to declare this or assign this variable data, because remember, anything that's declared bytes memory. Go. Zoom in? Oh, yeah. Oh, I thought so. It is not letting me zoom in. Yeah, sorry, this is not going to let me zoom in here. But I'll go over basically every line, so we'll step through here. So yeah, the data, basically what we're doing is storing that pointer to where the bytes are going to be. We're storing that. Next, we're going to store the length, the length of the byte array at this pointer. So at the free memory pointer, we're going to store bytes length. In this case, we're just going to store 4 bytes. It's going to be 1, 1, 2, 2, 3, 3, 4, 4. We're going to store that. Then in the next slot, we're going to, first we're going to increment the free memory pointer, right? So we're keeping track of this. We're keeping track of how much, how much memory is being used here, how much memory is being written to. So we're going to increment that by 32 bytes or by a single word. Then we're going to store at this new location the bytes that are going to be padded. They're going to be packed to the left. After this, we're going to increment the free memory pointer one more time. And we're going to store basically in the free memory pointer slot, we're going to store this updated free memory pointer, right? So basically, as we're incrementing this, we're keeping track of where the new free memory is. And then once we're finished with all of this, we're going to store it at the OX40 slot. Any questions?
Question. When you have solidity, when you resize the dynamic array, it moves in memory to the location essentially?
Right. So it's going to, again, let's say you append an extra byte to the end of this. It's going to store that extra byte at the end. It's going to keep it packed, and then it's going to increase the.
But say you have allocated something else in memory before pushing. That's what I meant. Like if you know there's something at the slot right after that array, and then you push, it will move essentially, right? All of it.
It should. I haven't tried that. We can actually try that as well. We can hop over to Remix and try that. Yeah, it would make sense if it would, right? Because then it would just get really, really confusing, right? Right. You're right. Sorry. Thank you. Storage.
Yes.
Right. So in Solidity, you do have to specify the length ahead of time. Thank you.
You have said that the dynamic size array and one slot for each element, right?
Right.
What if I have some kind of the structure that I want to create the arrays of them, and they don't fit on one slot?
So like a struct, like a memory struct. So memory struct. So struct actually acts similar to a dynamically sized value. So it's actually going to be a pointer to that as well.
Okay.
Right. Right. So whenever we store, so the first one we're storing the bytes length, right? We're storing the number 4. Even though it's just a single value, that's actually occupying a full 32 bytes. So we want to increment it by the full 32. Any other questions? Great. So next, we're going to have storage. Now, storage is actually going to be a few different cases here. First, we'll start with statically sized variables. So per Solidity's documentation, storage layout starts at slot 0. The data is stored in the rightmost bytes of that slot. Now, if the next value can fit into the same slot, obviously this is determined by type and the maximum value, it will actually be right aligned into the same slot. So you can actually pack variables into storage. You can do the same thing with storage structs. And then immutable and constant values that you see in the contracts, they're actually not stored in storage at all. So basically what these are is they're replaced at compile time with the exception of immutables. So if you have an immutable that can only be determined at deploy time whenever it runs to the constructor, it'll actually replace every instance of that in the bytecode. So as a quick example, we have a contract. It's got 5 values in it. First is going to be a full uint 256. So we want to occupy an entire 32-byte slot with this. Next, we have 2 values of 128 bits, so basically 16 bytes each. So these can actually be packed into a single slot, and we'll see that they are. So B is 2. It's here in the rightmost bit. And C is packed in the next rightmost place in that slot. And then we have, finally, 2 uint8s, which are stored here. All right, so everything is packed as tightly as possible in storage whenever we're doing this layout. Next, for dynamically sized variables, again, per the documentation in Solidity, a mapping slot is the hash of the key value concatenated with the storage slot. Right, so let's say, for example, in a balance mapping in an ERC20, it maps an address to a uint 256. Let's say it's in slot 0. What it's going to do is whenever you need to read or write to this, we're going to take that address, pad it to 32 bytes, concatenate that with another 32 bytes, which is the slot. It's going to be 0. And then we hash all of that, and that's where the actual value is stored. Now, dynamically sized arrays, it stores the current length in whatever slot it occupies, and then its elements are stored sequentially starting at the SHA-3 hash of that slot number. Byte arrays and strings are stored the same way as other dynamic arrays unless the length is 31 or less. If this is the case, then what's going to happen is all of that's going to be packed into a single slot, left aligned, and then the length of that is going to be packed, or is going to be placed at the rightmost byte. And it's going to be 2x the length. So looking at this one, we have 3 storage variables. We have a string, an array, and a mapping. So looking to the storage layout, first, over to the left, we have 61, 61, 61, 61. These are the 4 A's. And then over on the right, we have 8, which is 2 times the length. In the next slot, we're going to store the length of this data value. It's going to store 1 and 2, right? So what's going to happen here is whenever the code is executed, it's going to see that the length is 2 here at slot 1, and whenever it wants to access these values, it's going to hash slot 1, and that's going to point down here to OXB1, et cetera, et cetera. And then we can see here's the first value, and here's the second value. And then finally, we have the mapping. It's mapping an address to a uint 256. The actual storage slot of a mapping is always 0. That doesn't mean that it's not incremented. The storage is still incremented, but this slot is always going to be 0. And then any addresses that are mapped to, of course, will be that hash, right? So OXE9, et cetera, et cetera. So one more thing to mention, something that's really important to note, is storage in regards to inheritance. So Solidity uses C3 linearization. So basically, in the context of storage, what this means is storage slots in a parent contract precede the child contract storage. When a child has multiple parents, the order of the parent's storage is set by the order of inheritance. And this process is repeated recursively, and storage packing rules are still in play when applicable. So here we have a basic inheritance example. We have parent 0, it's going to store A, it's going to be 1. Parent 1 is going to store B at a value of 2. And then finally, we have child, which is going to inherit parent 0 and parent 1, and it's going to have its own value C, and that's going to be 3. And looking through the storage layout, first we have parent 0's storage, then parent 1's storage, then child storage. This is really important to note, especially with things like proxy contracts. You'll see in some of the Open Zeppelin implementations these storage paddings and things like this for upgradability. So next up, we have event logs. So per the standardization, event logs follow the following rules. They can have up to 4 topics. The first topic is always that hash of the event signature. So it's going to be the event name, parentheses, and any types. And then non-indexed topics are logged by storing them in memory and then passing to that log instruction a pointer to where that memory starts and how big that memory is. So as an event log example, at the top we have a hash, and that's going to be the event signature hash. Next, we're just going to have A and B, simple constants. Now in Solidity, this first function is how we'll log this, right? We say emit, the name of the event, and then any arguments that go to that event. Next, we have log in YUL. So this is actually what's happening under the hood whenever you do this in Solidity. So first we want to store, note that B is not indexed, so we want to store that in memory. And then A is indexed, so we're going to have that on the stack, right? It doesn't have to go into memory. So first thing we do is we're going to store B. We can just store it at slot 0. We're not going to be dealing with memory after this, right? The function's going to end. So we store at slot 0 B, and then we call the log2 instruction, and what we're going to pass to it is a memory pointer, in this case, slot 0 of memory, the size of memory, which is going to be 32 bytes, the event hash, which is going to be topic 1, and then the index topic A, which is going to be topic 2. So next we have errors. So per the standardization, an error consists of a 4-byte selector and some error data. Now Solidity actually has 2 predefined errors. This is error and panic. But since Solidity 0.8.4, developers can actually define custom error types where you can have names and arguments, and it's actually a bit more efficient than the standard require Boolean string. The reason for this is the Solidity defined errors. First is panic, and it's got a uint 256. So this is things like divide by 0, overflow, underflow. That's when the panic comes into play. Each one has its own code. It's in the documentation. And then next is the actual error. This takes a string in memory, and you can see. So first is a panic code. So we have these 4 bytes, which is the panic selector. And then the next 32 bytes is going to be the actual panic code. In this case, it's 1. Then the next one is going to be require, or what is standard with require. We pass it a Boolean. If it's false, it's going to throw this error with a string in it. Now note this actually takes up a lot more memory because we have the error selector. And remember, per the standards of strings, we first have to have a pointer to the string and then the actual string itself, right? So that's going to occupy extra data. Right, so basically because the error selector is only an offset of 4 bytes, that's actually not padded to the full 32. So right after those 4 bytes, we're going to start putting other data. Any other questions? Great. All right, so next we're going to do applied Yule plus Solidity. So we're actually going to hop over to Remix. And that's remix.ethereum.org. And from that link tree earlier, we actually have some boilerplate code here. Make sure this is big enough to see. So you might want to just copy paste this from that link if you're going to be following along, because lots of already pre-encoded data and all that kind of stuff. So I'll give you guys a minute to get that pulled up, copy pasted, all that good stuff. Okay, we'll give it just another second.
Is that your Canita soul is on the remix link that is displayed on the link?
Right. Yep, so that's going to have the code. It's going to be in a gist, but you can just copy paste that.
The remix link, there's a GitHub link. Yeah, you have to copy from the GitHub to the remix. It doesn't load automatically to the next page.
Yes, one moment. Maybe not. I'm going to write it right here. So it's going to be the link, linktr.ee/Ethereum assembly. Hopefully internet doesn't rug pull us here. All right, we'll go ahead and jump into it. So everything here that's predefined, this is just for the sake of us not having to go and encode stuff in hexadecimal and all of that, right in the middle of the workshop. So just looking through these constants really quick, we have the length of the name. In this case, the name is actually going to be Yule token. So the length is going to be 9 characters, and then in here we have padded over to the left the string. Next we have the symbol. That's going to just be Yule, Y-U-L, all caps. And so here we can see the length is 3, and these are the 3 characters for that string. After this, I went ahead and hashed the selectors for two custom errors that we're defining here. One is going to be insufficient balance, and the other is going to be insufficient allowance. Now, no insufficient allowance, we're actually going to pass an address of the owner and the spender in here, and this is going to give better error messages for client libraries and for users. So hopping into this, first thing we're going to do is we're going to define the name function. And we're going to make this pure. We're not storing anything in storage. We're actually just going to return a constant. I'm just going to return a string in memory. Okay. Now, what we're going to do, if we remember the standard for storing strings in memory, first is going to be the pointer. Then the next slot is going to be the length, and then the slot after that is going to be the actual data itself. So we're going to do 3 memory writes, and then we're going to return from that. So first we're going to mstore at slot 0. We're going to store OX20. And that's where the actual data is going to be. It's going to be a 32-byte offset. Next, we're going to store, oh, no, hold on, safety. Memory pointer, we want to load from memory. So we load that. Now, this actually should be fine in this case. Like, we know exactly where it is because nothing's been written to memory, but it is good practice as often as possible to use this free memory pointer. So we're going to load from OX40. Sure, yeah, so let's say, if you just start writing to the 0 slot, and in this case, we're going to occupy 3 slots, that's going to take slot 0, OX20, and OX40. So it's actually going to overwrite the free memory pointer. Now, in this case, we're actually returning from assembly, so we are safe here. But the problem is, if we're doing some assembly, let's say within a function, and maybe there's stuff that's happening after that, Solidity is going to trust that whatever value is in OX40 is the right value. So if we overwrite this to something strange, in this case, it would be the string padded over to the left, which is actually technically a massive number. This would actually consume a massive amount of gas and realistically probably revert. But yeah, so basically, as much as possible, we want to use, basically load whatever is at OX40. That's going to point, normally it starts at OX80, so that's after the 4 reserve slots. But again, for the sake of keeping it safe, we're going to do it like this. So we mstore at the mem pointer. We're going to store the length, or sorry, not the length, the OX20 pointer. After this, we're going to store 32 bytes later, we're going to store the actual length. So we're going to add the mem pointer and OX20. So we're increasing by a single word size. We're going to store the name length. Next, we're going to store at an OX40 byte offset.
Sorry, the first mstore shouldn't be storing mem plus 32?
You mean like after the first mstore?
In the first mstore, instead of 0x20, shouldn't we be storing the next slot after mem pointer?
No, so this is actually an offset from this value itself. So yeah, so the OX20 offset is just pointing to the actual length itself. So we stored the pointer, we're storing the length, and now finally we're actually going to store the data. And so what memory should look like right now is starting at the free memory pointer. We have the string pointer, the string length, and then the actual string. And so this is going to occupy 3 slots, which is OX60. So what we can do is return, starting at the mem pointer, we can return OX60 bytes. So very quickly, we're going to compile this. I'm on Solidity 0.8.17. We'll check that the compiler is 0.8.17. Everything's all good. So now we're just going to deploy this to a local virtual machine. And here we have the name function. Whenever we hit it, it's going to return Yule token for us. All right, so next we have the symbol function. It's going to do basically the same thing. The only difference being we need to store the symbol length and the symbol data. So first we load our mem pointer. Then we store in memory at the mem pointer the string pointer at an offset of OX20. We'll store the symbol length. And at an offset of OX40, we'll store the symbol data. And then same thing as before, it occupies the same number of slots because everything is padded. We'll return mem pointer OX60. Now note in this case, we're actually not incrementing the free memory pointer, and that's because we actually are returning from the assembly itself. If we were to break out and continue doing things, we would actually want to actually store what the new free memory pointer is. In this case, we would increment it by OX60. Next up, we're going to do decimals. It's going to return a UN8. So first, now in this case, we're actually not occupying very much memory at all. We're actually only occupying a single slot. So we can't actually just write to the very first slot, right? It's mostly whenever you need to write 3 or more slots that you want to actually do it at the memory pointer. In this case, we're going to do a little bit of a hack there to keep that in the lowest slot. So we mstore at 0, the number 18, because we're not bad people and use 6 as decimals. And then from there, we're going to return from slot 0 in memory. We're going to return OX20. Even though it's a UN8, it's stored at the rightmost bytes, so we need to return that full 32-byte word. All right. Now that we're done with all of that basic boilerplate stuff, let's go ahead and set up a mapping. This is going to be mapping an address to UN256. We're going to make this internal in this case because I want us to actually do it in assembly and see exactly what's happening. Obviously, we can just make this public and make it a lot easier, but we'll say internal underscore balances. Next storage slot we're going to need after that is going to be the allowances. So we're going to map an address to a nested mapping, which maps an address to a UN256. I'm just going to comment here what this is actually mapping to. Great. All right, so next we're going to do the balance of function. It's going to take an address. And we're actually not going to name this variable because we're going to manually load it from call data so we can see how call data is working, but it is going to take an address. It's going to be a public view function because we are going to read from state, and it's going to return a uint 256. All right, a quick time check. Great. Okay, so this is where it's going to get weird. Remember, we're mapping an address to a balance. And per the standard, what we need to do is we need to hash the address and then the slot in memory, or a slot in storage. In this case, it's 0, so we're going to pad an address, and then we're going to put 0, and then we're going to hash it. But the hashing function actually reads from memory, so we're going to need to use some memory to do this. So first thing we do is we're going to mstore. Actually, no. We're going to assign this variable for readability. We'll optimize a little bit in a moment. So first thing we want to do is get the, let's say, account. And so what we need to do is load the address from call data. Now, if you remember, the first 4 bytes are the function selector, and then the next 32 bytes are the first argument, in this case, our address. So what we'll do is we'll call data load, and we're going to do that at an index of 4. So it's going to take the next 32 bytes and put that into the account variable. Next, we're going to store this in memory. At slot 0, we're going to store account. And then at slot OX20, or at the 32-byte slot, we're going to store just 0. Next, we're going to get the hash, which is going to be kekak 256. And what this is going to take in assembly, now in high-level Solidity, what this is going to take is like a string or bytes, but in low-level Yule, it's actually going to take a pointer in memory and the size in memory. So in this case, we're going to start at slot 0, and we're going to consume 2 different slots, right? So OX40. So this should actually be the key to this person's balance. So what we can do from here is we'll say balance, and that's going to be sload. Oh, no, balance is a reserved word. Hold on. There we go. Account balance is going to be sload at that hash, right? So we're loading from persistent storage this slot. Next thing we want to do from here is we want to mstore. Now at this point, we're not actually going to need what's in slot 0 and slot slot 1, like 0 and 32 here. So we can actually just overwrite that with the account balance. Okay, and then finally, we're going to return. And so that's going to start at slot 0, and it's going to be OX20 bytes. So this is kind of like a more verbose version, so we can see exactly what's going on with variable names and things like that. But let's go ahead and do just a little bit of optimization and seeing like what you might actually see in production, right? So account is only used once, and that's loading here from call data, so we can actually just remove that and put that here, right? So we're storing in memory at slot 0, whatever's in call data starting at 4. Here we have this hash. Instead of declaring a new variable, we can actually just load that straight from storage. And then instead of declaring an account balance variable, we can actually just replace that as well. Right, and so now it should be functionally exactly the same. We're storing the first argument in memory at slot 0. We're storing the slot number in slot OX20. And then we're hashing that, loading from storage, putting that value into memory, and then returning from memory. And so this is the full process of what a balance of function is doing.
What is the body in the hashing function? Is it on parameter?
That's the length of memory so far. So these 2 slots. Sorry?
Because you have 2 slots, right?
Exactly, yeah.
The second half of
Exactly. Because it's in the first storage slot, we can do that at 0. Actually, something else we can do here, since this is already implicitly 0, we could remove that. But again, for the sake of safety, we'll just leave that for now.
I think I have seen that the assembly are just empty, it will not give an error. What then will be returned? Is it 0?
Return with like just parentheses?
Yes, without any code.
Right. So in this case, it's actually going to give us an error because it actually is.
The whole assembly code. Oh, it's empty. Yes, just the object. It's like basically, if you will not give a return statement, what will happen? What will be returned?
Oh, right. So like basically, if we don't say like return down here.
No return enter.
Oh, yeah. So in that case, it's actually not going to return anything. Like if we did this, it would actually like load from call data, load from storage, put it in the memory, but it wouldn't actually return anything to the caller.
But the function itself is declared to return something. I guess it would be new value of 0.
Right. So I mean, you can see here it gives us compiler warning. Let's see, unnamed return variable can remain unassigned. That's actually a weird one. Let's try that. It's going to give us a warning, but we're going to try it anyway. By the way, using Remix is a fantastic way to try out these little edge cases. If you're ever not certain how something works, this has been an invaluable resource to try these things out. So let's go ahead and give it a try. Balance of, we're going to need an address. We'll just copy this one. It returns a 0. Okay, so I guess in that case, if you don't explicitly return, then Solidity will actually insert a return statement for you, and it's just going to return nothing at all.
Okay, and the next question, what if I want to load from the call data only 1 byte? Not all 30 bytes, but only 1 byte.
So call data only loads, using call data load, it only loads 32 bytes. So in the case of like, for example, if you need to figure out what the function selector is, right, you can only grab the full 32 bytes. So in this case, you would actually use bit shifting. You would want to, those 4 leftmost bytes, you want to shift them all the way to the right.
And the rest will be still the same. It will not be like the carousel.
Right, it does not wrap around, they'll all be zeros.
So, yeah,
So just adding this alone shouldn't add any extra opcodes. This is just like a abstraction for the high-level language. But I believe we could actually just access it like this. So this and what we were doing a moment ago is actually functionally identical, right? So either we can like manually load from call data, or if we name the argument, we can actually just put that in there. Right. Yeah, because the function selector will be the same, and then if it's not actually used, it shouldn't consume. And I mean, of course, there will still be a place in the call data for it, but if we're not explicitly using that variable, then there's no point in which that's going to be loaded from call data by Solidity.
we are storing the length, storing data in then returning does that basically do that variable?
No. So what this actually does is, so the mem pointer tells you obviously where in memory to get the value, and then OX60 is the length. But what this is actually going to do in this contract, it's going to finish executing. It's going to stop executing, and then whoever called this contract, whether it's an EOA or another contract, it'll actually return that data. So it'll take that chunk of memory, in this case 60 byte or OX60 bytes from free mem pointer, and that's actually going to be returned into. It's going to be returned either to the client library, like Ethers or Web3.js, or it's going to be returned to another contract encoded as a string. Right. As soon as we call return, it's actually going to stop execution from there. So even if we put in anything after that, as long as it always returns, we'll never go there.
So each function has its own memory and stack when you execute, or they share across, like if you go, I don't know, in decimal, you go symbol, they share the same memory, or like execution.
Right, great question. So anytime that you call a contract, it's going to create what's called a context. And so this context is going to have a clean stack, a clean memory. It's going to be able to access the storage at whatever address is there, right? And then other contextual information. So basically, anytime a function is called on this, everything is a clean slate. So it's going to read and write from that same clean slate. And then once the function finishes, it stops and the memory is gone, right? So in this case, like, they're technically writing to the same storage slots, but they're never executing at the same time, so we don't have to worry about any kind of like memory overwrites or anything.
But it's an internal function shares, right? Because the internal function gets in line. Like if you're calling in the same contract, the internal function of the contract.
So if you call an internal, yes. So if you call an internal function, actually at compile time, this is a little bit confusing about Solidity, is that you have like public and internal functions. Public functions explicitly, take some information from the caller, and then it's going to return some information based on that. Whereas internal functions, there's actually what it does is it takes a number of items on the stack. Let's say your internal function takes 3 arguments. It's going to expect 3 values on the stack, and then it's going to operate on that. And if it returns anything, it's actually just leaving values on the stack. So inside of internal functions, whenever you return from that, it's not actually using the return instruction. It's actually just leaving it on the stack and jumping back to where it came from.
You said that every function starts with the memory state, but it seems that the memory function gets twice. Is that like a golden state as simple as
Right. So the first thing that happens during the execution of a contract, at least per Solidity, is we're actually going to store a free memory pointer. So like the first 2 slots, 0 and OX20, these are always going to start out as 0. OX40 is going to have that free memory pointer, and then the next slot after that, of course, is the 0 slot. So we don't put anything there. We can actually take a look briefly. If we compile this and we look at compilation details, so you'll notice the first few opcodes here, we're going to push OX80, then we're going to push OX40, and then we're going to mstore. And what that's doing is storing OX80, which is the first free memory pointer. We're storing that at slot OX40. And this is actually like a big telltale sign that a contract was written in Solidity. This always happens first. Every Solidity contract starts with 6.0, 8.0, 6.0, 4.0, 5.2.
You keep on feeding the memory, and utilizing the memory, doing all these further things, beginning of form, that sort of stuff, right? For example, instead of catch-up the memory we would operate on, if I use catch-up in another function and then catch-up in another function and the span function, if it was one function, actually you wouldn't need to extend memory. It could be used as storage, obviously, because more than catch-up.
So you mean like when you have multiple internal functions, or right? Yeah, exactly. So what Solidity actually does is those first 2 slots, the reason that they're kind of reserved is that's actually normally used as a sort of scratch space for hashing. So normally you're hashing 2 values together, so that's where we'll put that and then hash that together. Right. So per the standard of how strings are stored in memory, it's always a pointer to the string, and then the length of the string, and then the actual string itself. So in this case, it's kind of a formality, but it's really important to have that OX20 there, because whenever we return it, the client libraries expect it to be encoded as... actually, no, does that return that? We're going to try it. So let's call name. And what we can do here, this is another great way to look through transactions and find things you might not be sure about. Let's break this out. It's not going to let me make it bigger. Okay. Right. So what we'll do right here at the very end, let's take a look. So we have some memory laid out here, mostly zeros. It looks like, hold on. Let's step through this really quick. I really wish this would let me make it a little bit bigger here. So here's the state of the stack, right? In this case, we're going to push the free memory pointer, which is 0x80. We're going to push the length, which is 0x60. And what that's going to do is point to slot 0x80 in memory, which is going to be here. And it's going to go for 0x60 bytes. So here's the first, here's the second, and then here is the third. Right, so because this actually gets returned with it, client libraries are going to use this to actually decode strings. So if we didn't return this properly, it would actually throw an error. Like it wouldn't know how to decode it. It would just give you a bunch of bytes back, right? So in that case, it is sort of a formality, but it is important, to make sure that the client libraries know how to decode. I think there was one more question. Right.
So it's what we bring compatible with that. I mean, like you can call the name.
Call it internally. Oh, you mean like if I say like this dot name?
If you have a function here, put it on stack, and then put it on stack. And I'm just seeing memory instead.
Right. So we wouldn't want to use the return instruction inside of an internal function. Like if it's being called internally, I mean, you can use that, but just know that that's going to stop execution at that point, which is not what you want, right? Because that'll actually return back to the caller. So if you're trying to like return from an internal function, you're actually just jumping back to the main function, and then that's where the actual return instruction is going to be.
In the line 36, the ATM store like 20. Yes, that's an offset.
Right.
Okay, so where you're storing the data. Okay, so if you store the data, I don't know, the 60, for example, I don't know.
Yeah, so what that actually is it's 0x20 from that place in memory. Right. So balance, let's go ahead and put that return back. Okay. Next, we're going to do the transfer. And this is where it's going to get weird. We're going to have basically some conditional logic in here. Remember that overflow and underflow checks only happen in Solidity 0.8 and after. So basically anything before that and then anything assembly is unchecked, which means if somebody tries to transfer out more than they actually have, the EVM is not going to stop that from happening. It will actually underflow, roll back over to the very top, and then they're going to have some obscenely massive amount of tokens. So we want to make sure to check beforehand that the sender has enough tokens before they transfer out. So per the standard, it's going to be a non-payable, so we're actually just going to call it public, and it's going to return a Boolean. So first thing we want to do is load the caller's balance, right? So what we need to do is hash, that information that we did before. So let's say, we're going to mstore. One more time. So we're going to get the mem pointer by loading from memory. From the mem pointer, we're going to store the caller's address. In this case, we can get that by calling caller with parentheses. At the next slot, so mem pointer plus 0x20, we're going to store the balance slot, which is actually going to be 0. Then we're going to hash, and let's say caller balance. So we hash these two starting at mem pointer with a size of 0x40. And we're going to take that hash and use it to load from storage. So now we want to check and make sure that the caller's balance is at least as big as the amount. Now that we've done the call data loading, we're actually just going to do this for the sake of time. We'll say value and receiver, just to keep things succinct. So we want to check and say if less than, so if caller balance is less than the value to transfer, we're actually going to do some revert logic. So we're going to take insufficient balance selector. Now this actually isn't going to take any arguments, so all we really need to do is actually just store this one value. Again, at this point, we're reverting, we're about to stop execution, so we can basically just write to the 0 slot. This can't cause any harm. So mstore at 0, the insufficient balance selector, that's going to be that 4-byte selector padded to 32 bytes, and then we're going to revert. And revert actually functions the same way as the return instruction. So we're going to give it a pointer and a size in memory. In this case, we're doing the full OX20. I guess we could also just do OX04. And so that's going to revert with that. And this is good because whenever we revert with the selector, client libraries are going to have access to this ABI. It's going to see that there is this error called insufficient balance, and that's the selector. And then we can actually do some better error handling on the client side. Sometimes you'll see people revert with 0, 0, and that actually just reverts with nothing. And obviously this isn't super helpful. So as often as possible, even though it does take a long time and it is annoying, make sure to store proper error information. Okay, so from here, we know that the caller balance, like if we're at this point in the code, we know the caller balance is sufficient. So what we'll do is we'll deduct the value from the caller balance, and then we'll add it to the receiver's balance. Oh, just one moment. Perfect, just double checking. Okay, so we add these two together, and then we'll say, let's say receiver balance. Right, oh, right, vice versa, thank you, sub. Okay, so next we want to get the receiver balance, and so we'll do this in a similar way. New caller balance, thank you. Sweet. Okay, so to get the receiver balance, we're going to do the same thing, except we're actually going to use the receiver as opposed to the caller. Again, we're not going to need these 2 slots of memory anymore, so we can actually just overwrite these. Okay. And OXOO. So the receiver balance is going to be what we load from storage, which is going to be the hash starting at mem pointer and of size OX40. So this is where we get the receiver balance. Actually, let's do this. Caller balance slot, because we're going to need this later. So let's take this, and we're basically just going to create a variable with this, right? Same thing. Great, so functionally identical, but now we can actually access the slots a little bit later whenever we need it. So now we want to get the new receiver balance. Again, we'll optimize a little bit later. New receiver balance is going to be sub. Sorry? Thank you. There we go. Okay, so subtract from caller balance, add to receiver balance, the value. Okay, so now we have our new balances set up. We've done the addition, the subtraction, so now we just need to store these back into storage. So we'll say store. We need the key and the value. In this case, the key is going to be the caller balance slot, and the value is going to be new caller balance. And same thing. Receiver, balance slot. New receiver balance. All good. Cool. Yeah, so just as a quick review of what we're doing with this transfer, loading the free memory pointer, we're going to store at that memory pointer the caller, then 0, because that's the slot of the balance mapping. We're going to hash that to get the slot. We're going to load from it to get the caller balance, assert that it actually does have the balance that it needs. If not, we're going to revert. Then we're going to decrement or decrease the new caller to the new caller balance. Then we're going to do the same thing for the receiver. Obviously, we don't need to check for the overflow. We're going to check that a little bit later. But we can be certain that this is not going to overflow. So we'll increase the receiver balance to give us our new receiver balance, and then we'll store that in storage here. So last thing we need to do after all of this is we need to return to the caller a Boolean. In this case, we're going to return true. So the way we do that, again, doesn't matter now, we're at the end of the execution, so we'll store at slot 0 OX1, which will be our true value, and then you can return those 32 bytes. The log? Yes, the log. Thank you. Okay, so we're going to have a transfer event. Probably should have hashed this as well, but we'll get those hashes in just a moment. So it's going to be a transfer event. We're going to have an indexed sender, an indexed receiver, and an amount. Great. So per the rules that we mentioned earlier, we're going to have, so this is going to actually be log 3, right? We're going to log the event signature, the event hash. Then we're going to log the sender as a topic, the receiver as a topic, and then the amount, because it's not an indexed topic, we're going to put that in memory and then basically pass the pointers to the log instruction. So I'm going to quickly, oh wow, so small. Great. So another place that you can do this if you want to get this stuff online and you might not have, if you might not have Cast installed on your local machine, what you can do is go to this online hashing tool and you can basically punch in this stuff. I think internet is going to rug me once again, but oh no, there we go. Cool. So we can just say transfer. And then same thing, right? So OX, DD, F2, et cetera, et cetera. All right, so we're going to set that as a constant. All right, I'm going to add some comments in here. Just a moment. Okay, we're going to store and now log. Okay, so before we do any of the logging, remember we have to store the amount into memory. So in this case, again, execution is about to end, so we don't have to be too careful about where we put things in memory. So let's go ahead and mstore at slot 0 the amount. I think in this case we called it the value, right? So we're storing that in memory, and now we want to call log, but remember we want to have the 2 indexed arguments and we want the event signature, so that's going to be log3. First thing we want to pass is the pointer in memory. It's going to start at 0. The size is just going to be this one value, right? Everything else is going to come from the stack. We just need these 32 bytes at the beginning. Then we're going to say transfer hash the next topic is going to be the caller. And then the final topic is going to be the receiver. Great. So at this point, we handle the balances, update the storage, log the event, and return.
Just 1 second. Just if you go log n, the values parameter emit log are always stored in the demo.
The values in the log, only the non-indexed. So the actual indexed arguments are on the stack, and then the non-indexed are in memory. Which also, I believe this is also in the link tree, the full like Yule documentation, basically everything you need to know about this. It's also going to have our log instructions in here, right? So log 0, 1, 2, 3, and 4.
Add another statement and to check the receiver of the caller that there will be no bug where you can give yourself a lot of fun, because when you will see you're storing the value of the receiver after you are storing the value of the caller. So basically I will give myself 100 more ethers or any kind of graph here. I can just add to myself a lot of money. I would say, because you are adding the new value based on another adding to greater than.
So if it's the same, it uses the same slot. It first increases, right? No. So whatever the value is at that slot, it will decrease. Then it loads, increases. Oh, yes. Okay. Right. Right. Great catch. Thank you.
Well, but now I can only lose money. I will do this. So you will give the reverse statement that will check if you
Right. Yeah. So let's do that as well. So let's just say equals if the caller is equal to the receiver.
Why do you lose money? Does it become 0?
No, because at first you will
Subtract,
yeah.
load, add.
Subtract, store, load, add, store.
Yeah, so
right. Oh yeah. So it evens out.
Yeah. I mean, it's better to check for sure, but I was curious if I don't understand it right. Okay.
Right.
Yeah.
Yeah. Great. Yeah. For the sake of time, we're going to be bad developers, and we're just going to revert with 0, 0, and we're just not going to tell anybody about that. All right. All right. Great. Good catch. Thank you. So after transfer, let's do allowance. No. Yeah, let's do allowance. Great. Okay. So in this case, what we need to do is, all right. So we're going to take the owner, we're going to map that to a spender, which then we map to a number. So the way that this works in storage is we're going to hash the owner and slot. Make sure I get this right. Owner and slot, and then the result of this will hash again. So owner, slot, hash, then the final key. Let's double check the documentation, make sure we get that right. Great, so here is the standard function, and then nesting that would be right. Right idea, wrong order. So the mapping rules are applied then recursively. So we're going to bring that down here so we can remember. Okay, so first we're going to do the inner hash. So we're going to mstore the owner. Yep. We're going to mstore the owner at slot 0. We're going to mstore at the next slot, the slot, which is going to be 0. Inner hash is going to be SHA-3 hash of the first 2 slots. And then we're basically going to do the same thing again with the inner hash. Wait. Slot 1, thank you. Okay, and then spender. Okay, the allowance slot then is going to be the hash of these once again. Okay, and so now what we want to do is load from storage. And then we want to store this in memory and return that back to the caller. Oh, whoops, not caller, owner. There we go. Okay, so we hash together to form the first slot, and then we hash again to form the second slot, this mapping. We load from that slot, put that in memory, and then we return it from memory to the caller. So next thing we want to do is going to be approve. Okay. So in the interest of time, we're going to copy paste, as all good developers do. Okay, so we're going to do the same thing. So the hashing, figure out the slot, and then from here, we want to set the value at this slot to the new amount. So store at allowance slot the amount. Next thing we want to do before we return is we want to create a log, and that's going to be the approve event. It's going to have an owner, a spender, and an amount. And so functionally, this is going to be the same as the transfer. We have 2 indexed arguments, so it's going to be log3, and we'll have to store the amount into memory. Great. Is it approve or approval? It's just approve? Just a moment. Approval. Great. So that's going to be approval. So from here, we'll take this hash. Make sure that's hex. Okay, so before we log the event, again, we want to store the amount in storage, and then we want to log 3. We'll start at slot 0. It's going to be of size OX20 because it's just the amount. First topic is going to be the approval hash. Next one is going to be the owner. In this case, that's going to be our caller. And the final one is going to be the spender, the person who can spend on their behalf. Okay, now that we've logged the event, last thing we want to do is store 1, which for true. Then we want to return that full amount. Great. Easy.
That's like the function returns like satisfied by judgment amount.
Right. So on the lowest level, a Boolean is actually represented as basically a uint8 that can only be 0 or 1. So it just occupies a single byte. But in this case, we're returning the OX20, just returning the full word. Okay, we're going to do transfer from. So this is going to have a sender, a receiver, and an amount. All right, so we're going to do a very similar thing to the transfer from function. We're actually going to just copy paste most of this with an exception. Oh, I don't know if I'm going to be able to do this with this tiny mouse. Hold on. Nice. Okay, no, we're just going to do it from scratch. We'll do it live. Okay, so we'll load the mem pointer. We want to generate the slot first for the approval. So we'll do the same thing as here. Just a moment. Owner, it's going to be... Okay, so the owner in this case is going to be the sender, and then the spender in this case is going to be the caller, right? So basically we want to check, what we're trying to load here and what we're trying to see is the spender's permissions on behalf of the sender. We'll call that caller allowance. Okay, we're going to load from that slot. And so basically we want to do the same thing. We want to check and make sure that caller allowance is not less than the amount, right? So if it is less than, then we're going to revert. In this case, we're going to be storing the insufficient allowance error. So notice this is going to take 2 arguments. That's going to be the owner and the spender. Since we're going to be storing a bit more information here, even though it is going to end execution, again, formalities. Mem pointer. So we're going to store the insufficient allowance selector. So that's going to be the first 4 bytes. Now remember, it's only 4 bytes in memory that we're occupying here. We actually want to write after this the next 32 bytes. So instead of adding a full OX20, we're actually just going to add OX04, right? So it's going to be the 4 bytes, then the next 32 bytes, and then the next 32 bytes after that. So storing at this slot, it's going to be the owner. In this case, that's going to be the sender. And then the next one is going to be one second. So the next one is going to be the actual caller. So notice we're still increasing by OX20 at this point, but because it is at an offset of 4, first slot is going to be the mem pointer. The next one is going to be mem pointer plus 4, and then the next one is going to be the mem pointer plus 4 plus 32. And so this is our entire chunk in memory where the error is. So we're going to revert starting at the mem pointer, and then it's going to be OX, 4, 24, and then 44. So OX44. And so that's going to basically assert that they actually have the allowance to spend there. So now that we've done that, let's go ahead and, oh, come on. Great. So next thing we want to do is we want to get the balance slot from the sender. Balance, thank you. There we go. Okay, so doing the same thing. My God, hold on. This compiler is being obnoxious. We're just going to do this. This is not actually important. I'm actually just doing this so the compiler doesn't give us all this yellow text everywhere. We're going to get rid of that in a moment. Okay, so we're going to load the sender's balance. Basically, again, we're storing the sender, storing the actual pointer in memory where this, or pointer in storage where this is going to come from. We're going to hash that to get the slot. From the slot, we load the balance. Then we want to assert that it is at least that amount. Otherwise, we'll revert with insufficient balance. Then we will store at the sender balance slot the sum of sender balance and amount. Great. Next, we'll do the receiver. So basically the same thing. Okay. And then we will store, whoops, inverse. Great. So same thing as before. Basically, once we pass this approval check, we're going to check the balances, make sure that it's all good, send all this stuff through. Last thing we want to do before we return is we want to do the log. So again, mstore at 0, the amounts, log, come on, 3. It's going to start at slot 0, offset of OX20. Transfer hash is going to be the first, second is going to be the sender, and final is going to be the receiver. Oh, and one last thing before we do this, before we return, is we want to make sure we decrease the allowance if it is not the max UNT256 value. So if it is less than, we're checking not sure of a good way to get this max value in assembly. 1 second. No, we're gonna have to log that or something. Sorry? OX, sorry? Right, yeah. I didn't want to have to do it that way, but it looks like I'm going to have to. You could underflow, which that is one thing that works, but also that does add, like that is computation at runtime. Best way. All right. And the reason that we actually can't just use, so normally you could do something like type uint256.max, but this actually is disallowed in assembly because this is a higher level functionality. So we'll just do that. Great. So if the caller allowance is less than this enormous value, what we want to do then is decrease the caller allowance, and we'll store that back in the allowance slot. And again, since we already checked to make sure that they have sufficient allowance, this should never underflow. Okay, then finally, we're going to store true. And then we're going to return it.
That if data just wrote max value less something, but when is that or when is that not true?
Right. So there's a common pattern. It's not part of the standard, but this is something that I'm seeing increasingly. Basically, to give like an infinite approval, you could just set it to the max uint256 value. And so instead of actually having to do like math on that, right, we can just check that. Right. So if less than, then we store. So that's all good. All right. So just reviewing this one function one last time, we're going to generate the allowance slot. Check the allowance, make sure it's sufficient. If not, we revert. If it's less than the max value, we're actually going to decrease the caller allowance. Next, we want to make sure the sender balance is sufficient. If not, we revert. Then we want to subtract from the sender balance this amount. Then we want to add to the receiver balance this amount. Then finally, we're going to log and then return true.
165 and 201 at slots are reversed.
165.
At 0, the center slot 0.
Right. So this is to generate the hash. So we're storing at slot 0 the sender. And he said the other was 205? 201? Yeah, same thing, right? So at the memory pointer and then at the memory pointer plus OX20. Right. Okay, so we have transfer from, we have approve, we have allowance, we have transfer, balance of, total supply. And again, we're just going to keep this internal just so we can, for the sake of the exercise, write this out. Now, of course, all of this that we're doing here is like very much over abusing assembly. And in general, you don't want to use it this much. This is just to give like a good picture as to like what's actually happening under the hood here. So total supply is going to be a public view function. Okay. Now this one's actually going to be really easy. Basically what we want to do is store the value at this slot. Now this is slot number 3, or slot OX02. This is OX00, OX01, OX02. So we can mstore at slot 0 the value that is loaded from OX02. Then from there, return OX00, OX20.
You need a mint.
A mint? Right. So I was actually going to do that in the constructor. But if we want to do a mint function, we could. Well, actually, are we short on time? Oh. Right. Yeah. So it's always 0. Best token. Was there another question? Transfer from? Hash 3 slots at the same. Oh, right. So if you want to hash 3 slots, then the first argument would be where in memory it is, and then you would just say OX60. So that's 3 slots. In this case, we're only ever hashing 2. That's just per the Solidity standard. But you could hash bigger stuff. Not quite. So the reason that we did the separate hashing here is because the second time we hash, we're actually concatenating the caller and the first hash, like digest. So it has to be 2 different hashes. All right. So in our constructor, we will once again abuse assembly. So basically, what we'll do here is we'll just do a static total supply for the sake of simplicity. We're going to store into the caller slot the initial supply. So first thing we want to do, mstore the caller. Next is going to be the slot for balances. And we're going to store at the slot total supply. What do we want to call this? Max int. Yeah, I like it. Cool. All right, so we'll do that. Now, since this is kind of technically a transfer from the 0 address, we'll go ahead and log an event for this as well. So mount, we're going to store into memory. And then from there, we're going to call log3 transfer hash. No. Log3 memory pointer. It's going to be 0. Memory size. It's going to be OX20 to store that value. Transfer hash. 0 address. We can just say 0 here. Then receiver. And all 3 topics. Perfect. Now from here, we're not going to return because in the constructor of a contract, the way that a contract is actually deployed to the chain is we take the entire contract's bytecode and then some. And basically what we're doing is returning the entire contract's bytecode. Like we're putting the whole bytecode in memory and then calling return on that. That's how the actual deployment process works. And part of the reason why deployments get so obscenely expensive because memory memory expansion gas costs scale quadratically. So it gets very, very expensive. But the reason that I bring this up is we're not going to call return here because a constructor needs to do its job and return the bytecode at the end of this constructor's execution. So everything compiles. Moment of truth. Whoops, hold on. All right, so first let's check decimals. Should be 18. Name should be Yule token. Symbol should be Yule. Total supply. We did not increase the total supply. Lol. So store, that's going to be slot OX02, and it's going to be max UNT 256. Great. Good coin. Great tokenomics. All right. Total supply. Now it's this enormous number. And let's do a quick transfer. We're just going to transfer to some random address. Who cares? No. First, let's call balance of on this address just for the sake of seeing what's what. So balance of, this should be the deployer's address. Is it not? Just a moment. Interesting. Caller OX00. Caller OX00. That's it. Okay. There we go. One more try. So balance of here, our enormous number. And then finally, we'll just make a quick transfer here for, let's say 10, because we're stingy. And then we call, and the balance is now 10. And that's an ERC20 token written purely in Yule. And that concludes today's workshop. So really quick, these are some other resources that you guys can check out. Educational resources, EVM codes, obviously the yellow paper if you're a degenerate and you're into that kind of thing. Developer tooling and languages, Huff language. This is basically a low-level assembly language that will teach you a lot about the EVM. The Foundry development environment, really good for testing and trying things. And the Remix browser IDE for that local testing in the browser. You had a question?
Transfer from can be used simply to know why it was called, like not called it. For example, call the ruler as a user. Can we know if it's add liquidity or if it's a swap that causes the transfer from? Can you get called it?
Add liquidity or swap. So that's not possible now. Right, because all it has access to is like the message sender, right? Now maybe. Right. Any other questions?
The compiler is smart now, so I will, let's say, use the well-checked open settlement implementation, which what we will do as the Solidity developer. Is the compiler smart enough to declose the gas use as this implementation?
So. Right, so some things are trivial, but some things you can actually like very heavily optimize, and that's actually why a lot of people tend to use assembly. Like for example, take ABI.encode. So this is actually like fairly gas intensive, especially like let's say you want to loop a number of external calls. It's actually ABI encoding every time, right? And there's like a lot of gas that's being consumed there. Whereas like maybe you're calling the same function over this entire loop. Instead, maybe what you could do in assembly is you run that loop, but let's say instead of doing this encoding the entire time, every single time, you just store it once and you kind of like cache that, right? And so things like that will actually give you massive improvements in gas efficiency.
Okay, so compiler is not always, it's not that well written, so it will do this kind of thing every month.
Right, it is improving. So a little bit about the state of the Solidity compiler. Originally, Solidity used its own pipeline, so it would go from Solidity to intermediate representation to bytecode. Now there's actually a migration happening where basically Solidity will compile to Yule, and then we can actually use Yule's pipeline to optimize because the Yule optimizer is very well developed. This was actually sort of the original reason of using Yule, is that like many high-level languages could compile to Yule and have the same, basically intermediate representation where everybody can take advantage of the same optimizer.
Okay, thank you very much.
Welcome.